Methyl will be the smaller one. So that will be considered as the alkoxy. So this will be methoxy. And how many carbon atoms are here? 1, 2, 3. So it is propane. What are protic acids which can release H+, right? Like H2SO4, H3PO4, that is sulfuric acid or phosphoric acid. Dehydration of alcohols, if you are doing for a secondary or tertiary alcohol, you are going to get alkenes. Okay, elimination will take place instead of substitution. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 8, that's the last session of the chapter, alcohols, phenols and ethers. So till now we have discussed completely regarding alcohols as well as phenols, right? That is, in the last session we discussed electrophilic substitution reactions of phenols, right? Nitration, halogenation, Kolb's reaction, Riemann-Tiemann reaction, oxidation of phenols, all of that were discussed in the last session. So by that we came to an end to the discussion of alcohols and phenols. So in today's session we are going to study completely about ethers. Again, the introduction, nomenclature, its physical properties as well as chemical properties, and we'll come to an end to this chapter, right? So in today's session, classification, we'll study nomenclature as well as methods of preparation of ethers, right? So let's see. First of all, what are ethers? Ethers are alkoxy or aryl oxy derivatives of hydrocarbons. So it is alkoxy or aryl oxy derivatives of hydrocarbons. So phenols, we know that from hydrocarbons, one hydrogen will be replaced by a hydroxyl group. This is the general representation for an alcohol, right? Now, if it is phenol, instead of alkyl group, it will be a aryl group, right? It will be aryl group. So this was your phenol. Now, what is ether? Ether is in this format. Okay, so you can see this oxygen O, that is your functional group, and on either side you will have alkyl groups or aryl groups. So this O is what is written here, alkoxy or aryl oxy, based on whether the R is alkyl or aryl group, right? So where R and R dash can be aryl or alkyl group. Okay, now the classification of ether, it can be classified into two types. One is simple or symmetric ethers. Now what is simple or symmetric? So symmetric, what does that mean? Something is symmetric there, right? So the general representation is already shown here, RO, R dash. Right. So symmetric ether means this R and R dash will be the same. Either it will be the same alkyl group or same aryl group. Okay. So that is symmetric. The ether in which the oxygen atom is bonded to two identical alkyl or aryl groups, they are called as simple or symmetric ethers. Right. As you can see, this is the oxygen atom. On either side you have ethyl and ethyl group. Okay. So this is what? This is a symmetric alkene. Now here you have on both sides phenyl group. So this is called as diphenyl ether and this is called as diethyl ether. So naming we are going to study in the upcoming slides, right? Now the next one is mixed or unsymmetrical ether. Now what is mixed then? Yes, of course, the both alkyl groups or aryl groups will be different. That's it. The ethers in which oxygen atom is bonded to two different alkyl or aryl groups. So you can see one example here. In one side it is methyl group, other side it is ethyl group. So this is called as ethyl methyl ether. Okay. So here in both sides of the oxygen atom, it is bonded to two different alkyl groups. So hence it is an unsymmetrical ether, right? Now we are moving on to the nomenclature of ether. So the basics of IUPAC nomenclature you already know. So specifically for ethers, we are going to see when ether functional group is present, how are we going to name it? So for alcohol, we know that it has to be ended with, that is the suffix is all. For phenol, it is going to be ended with phenol. All of that we have discussed. Now for ethers, in common system, the ethers are named by adding the suffix ether. So you're going to end it with the name ether itself in common name, okay? After naming the alkyl or aryl group in the alphabetical order. So as discussed, oxygen will be in the center and then you will have two alkyl groups or aryl groups, right? So first you have to name the alkyl or aryl groups according to the common system. Name the alkyl or aryl groups according to their alphabetical order. Then end the name with the suffix ether. Clear? Now in the IUPAC system, ethers are named as alkoxy derivatives of alkanes. Okay, so the principal name or the principal chain will be your alkane itself, right? And it will be prefixed by alkoxy based on which alkyl group is there. So once we go through these examples, it will be clear for you. So the first one you can see here, it is CH3 OCH3. So as you can see, it is a symmetric ether which is present here, and on both sides you have methyl group. So how do you write the common name? As discussed, you have to name the alkyl or aryl group and then end it with ether. So which is the alkyl group here? It is methyl. And how many are there? 2 are there. On either side you have 2, right? So it is dimethyl ended with ether. That is the common name. Okay. IUPAC, how do you write? So what is the total number of carbon atoms here? It is 4. So how do you name the same compound in IUPAC nomenclature? Let's see. So it is written here alkoxy, right? How do we have to name it? It is alkoxy derivative of the hydrocarbon. So if we are considering this as the alkoxy group, okay, alkoxy means oxygen and the alkyl group, that is alkoxy, okay, alkyl group and oxygen. So this is your alkoxy group. Which one it is specifically? This is methoxy, and this is your hydrocarbon. Which is the hydrocarbon from which this has been derived? This ether has been derived from CH4, right? Methane is that hydrocarbon from which one hydrogen atom is replaced by an alkoxy group. So the name will be methoxymethane. Methoxymethane. Moving on to the next one. On either side you have ethyl group. So this is diethyl, yes, ether, right? Common name is diethyl ether, of course. Now what will be the IUPAC name? Again, this is the alkoxy group which is ethoxy, and this is your hydrocarbon which is ethane, right? So it is ethoxyethane. I hope it is clear. Next one is CH3O, CH2, CH2, CH3. So this is an unsymmetrical ether. On either side you are having different alkyl groups, right? So you have a methyl group as well as a propyl group, right? You have methyl as well as propyl. So how are you going to name it according to common system? So you have 2 different alkyl groups. So when you are going to name it according to the common system, it has to be named according to the alphabetical order. So you have methyl and propyl. So of course methyl will come first in the alphabetical order. So you will write methyl propyl ether. Methyl propyl ether, right? IUPAC nomenclature, how do you write it? So this will be the smaller one. Which will be the smaller one? You have methyl as well as propyl. So considering these 2, yes, methyl will be the smaller one. So that will be considered as the alkoxy. So this will be methoxy. And how many carbon atoms are here? 1, 2, 3. So it is propane, right? So it is methoxy propane. So you can write it as 1 methoxy propane because it is on the first carbon atom, right? The alkoxy is on the first carbon atom. Moving on to the next one, that is C6H5O CH3. Now what is this? You have an aryl group here. So what is the structure of this actually? You have the benzene ring and you have OCH3. Now what is the common name of this? Methyl phenyl ether. So this is your phenyl, this is your methyl group. Okay. So again, according to the alphabetical order, methyl will come first. So it is methyl phenyl ether, and the common name also, you can also call it as anisole. So anisole is most commonly used. Now IUPAC name, how will you name it? So again, it will be methoxy and benzene, right? It will be methoxybenzene. So anisole can be also used as the IUPAC name as well. The next one is C6H5O CH3CH3. Now what is the CH3CH3? It is C2H5, right? Okay. So I hope it is clear. So now what will be the common name? It will be ethyl phenyl ether. Which one will come first in the alphabetical order? Ethyl. So it is ethyl phenyl ether, and IUPAC name will be, which is the alkoxy group, it is ethoxy. It will be ethoxybenzene. Clear? Next one is C6H5O CH2 6 times CH3. So here this much part is heptyl. As you can see here, you have 6 carbon atoms plus this one, that is 7 carbon atoms on this side, which is one of the alkyl group, and here you have C6H5, which is your phenyl group, right? So comparing phenyl and heptyl, heptyl will come first in the alphabetical order. So this is heptyl phenyl ether. Clear? Now IUPAC name, how would you write it? It will be 1-phenoxyheptane. 1-phenoxyheptane, because this is 6 carbon atom, this is 7 carbon atom, which is a smaller one. Phenyl will be smaller one. So this we are going to consider as the alkoxy. So that will be phenoxyheptane. Clear? Now moving on to the next one, CH3O CHCH3. And you have on the second carbon atom a methyl group. So from here what you can understand, on one side you have a methyl group, on another side you have this, okay, which is isopropyl, right? Isopropyl, why? Because the methyl group is present on the second carbon atom. So how do you name it according to common system? It will be isopropyl methyl ether. So this is your isopropyl, this is methyl. Isopropyl methyl ether. The next one is the IUPAC name. So what it will be? It will be 2-methoxypropane. Now why it is 2-methoxy? This is your first carbon atom, second carbon atom. On second carbon atom you have this methoxy, right? Alkoxy, which is methoxy specifically here. So 2-methoxy, and which is your major or a principal chain? It is propane. Clear? Now moving on to the next one, C6H5O, CH2, CH2, CH, CH3, CH3. So this is also an isopropyl group, right? So it is isopropyl because it is on the second carbon atom. So isopropyl, what it is? It is isopropyl pentane, right? So moving on to the next one, C6H5O, CH2, CH2, CH, CH3, CH3. So here also the methyl group is on the second carbon atom. So this is also an iso. Now how many carbon atoms are there in total? 5 carbon atoms. So this is isopentyl, and isopentyl you are having, phenyl you are having. So this is isopentyl phenyl ether, right? According to the common name. Now IUPAC name, how would you write? It will be 3-methyl butoxybenzene. So it is first, second, third, fourth carbon atom. On the third carbon atom you have one methyl group as well, right? So that 3-methyl you have to write, and this much part is your alkoxy group, because comparing 6 carbon atoms, this is only having 4 carbon atoms. So this will be butoxy, right? Butoxy, and that is benzene. Clear? Okay. Now the last one is you have a cyclohexane here. It is not benzene because there are no double bonds here, right? This is what? This is cyclohexane, and on the first carbon atom you are having 2 methyl groups, and on the second carbon atom you are having an alkoxy group. So this is your alkoxy group, OC2H5, because this is the bigger one, right? 6 carbon atoms are there. So this is going to be your smaller one. So what will be the IUPAC name? As you can see, this will be ethoxy, right? So on which carbon atom is there? On the second carbon atom. So it is 2-ethoxy, and on the first carbon atom you have 2 methyl groups. So it will be 1,1 dimethyl cyclohexane. So this is cyclohexane. On the second carbon atom you have the alkoxy, which is ethoxy. So 2-ethoxy, 1,1 dimethyl cyclohexane. Clear? Right. Now moving on to the structure of ether functional group. So in ethers, the 2 bond pairs and 2 lone pairs of electrons around oxygen are arranged almost in a tetrahedral arrangement. The carbon-oxygen-carbon bond angle is 101.7 degree in methoxymethane is slightly greater than the tetrahedral angle due to the repulsive interaction between the 2 bulky groups. So the carbon-oxygen bond length in ethers is almost the same as that in alcohols. So what does this mean? Generally, we are taking methoxymethane here. So that means oxygen is there and you have carbon here, another carbon here, and CH3 is here, CH3 is there. Methoxymethane we are taking. Okay, on both sides you have methyl group. So oxygen is having 2 bond pairs as well as 2 lone pairs. So according to VSEPR theory, we know that lone pair, bond pair interactions will be there. So repulsions will be happening. So as you can see, 2 lone pairs are there, 2 bond pairs are there, means actually the geometry is supposed to be tetrahedral. Because of the repulsions which is taking place between these lone pairs as well as between the lone pair and bond pair, there is a slight increase in the bond angle, which is supposed to be 109 degree. What it is happening? It is increasing to 111.7 degree. Clear? This is the bond angle of ether. Okay, so that is important to remember. And as you can see, the carbon bond angle will be 141 picometer in ethers, which is almost similar to that in alcohol, which is 142 picometer. Clear? Now moving on to the different methods of preparation of ether. First one is by dehydration of alcohols. So we already know what is dehydration. Removal of water. We are going to remove water from alcohols. So alcohols undergo dehydration in the presence of protic acids. Now what are protic acids? Which can release H+, right? Like H2SO4, H3PO4, that is sulfuric acid or phosphoric acid. The formation of product depends upon the experimental condition. When excess of alcohol is heated to 413 Kelvin in the presence of concentrated sulfuric acid, ethers are formed. Okay, so you have to take excess of alcohol, right? So alcohol is taken. Okay, 2 moles of alcohol is taken. So now what is happening? Water is being removed from here. So as you can see, OH and H. OH from one molecule and H from another molecule is removed under sulfuric acid and 413 Kelvin. What will be left when ROR? So ROR is your what? Ether, and water will be removed. So it is simple, right? Now hence ethers are called as anhydrides of monohydric alcohols as well. Now when excess of ethyl alcohol is heated with concentrated sulfuric acid under the same condition, we are going to get diethyl ether. So specifically we are taking an example of ethanol here, C2H5OH, another molecule of C2H5OH. Okay, now what happens? OH and H will be removed, that is water is removed. So you have C2H5O, C2H5, which is diethyl ether. Okay, so this is dehydration of alcohol. Clear? Now, this method is suitable only for the preparation of simple ethers by primary alcohols. When alcohol is secondary or tertiary, elimination takes place instead of substitution to give alkenes. Okay, so dehydration of alcohols, if you are doing for a secondary or tertiary alcohol, you are going to get alkenes. Okay, elimination will take place instead of substitution. Okay, now the next method is Williamson's ether synthesis. Williamson's synthesis, which is very important. Okay, so when sodium alkoxide is heated with alkyl halide in alcoholic medium, ether is formed via SN2 mechanism. So in detail we have studied about SN1 and SN2 mechanism, right? So this reaction is called as Williamson's synthesis. So you can see here alkoxide, sodium alkoxide is taken here, that is RO Na. This is sodium alkoxide. So this RO minus is called as alkoxide and sodium is there, so sodium alkoxide, which is made to react with alkyl halide. So this X you can see it can be chlorine, bromine, iodine based on which halogen you are going to take. Now what happens here? The sodium and the halogen will be removed as the sodium halide. It can be sodium chloride, sodium bromide based on which halogen you are using. Now what is there? RO, R dash, again you are getting your ether according to SN2 mechanism. Okay, I hope it is clear. Now, when sodium methoxide in alcohol is heated with methyl iodide, dimethyl ether is formed. Okay, so we are taking sodium methoxide CH3ONA and we are using methyl iodide CH3I we are taking. Again, what is going to happen? Sodium and iodide will be removed as sodium iodide. So you will have CH3OCH3, that is dimethyl ether or methoxymethane. Now this method is useful for the preparation of ethers containing substituted alkyl groups, that is secondary or tertiary. The reaction involves SN2 attack of an alkoxide ion or a primary alkyl halide. So that it means it follows SN2 mechanism, which in detail we have studied in the last chapter. Right. Now, so here we have taken a tertiary alkoxide. So you can see this is your alkyl halide and we have taken CH3, which is tertiary sodium alkoxide, ONA. So now what happens here? Because bromine is more electronegative, it will take up the shared pair of electrons towards itself. So this shared pair of electrons now it is with bromine and bromine will combine with sodium and form sodium bromide. Now what is here? Oxygen will donate its electron to the carbon because now carbon has got a partial positive charge, so that the oxygen will form a bond with the carbon. So what you are going to get? That CH3 and O will form a bond and sodium bromide will be eliminated. So tertiary alkoxides also undergo Williamson's synthesis. Now in this method, better results are obtained if the alkyl halide is primary. Alkyl aryl ethers can be prepared by treating sodium phenoxide with alkyl halide. When sodium phenoxide is heated with methyl iodide, methyl phenyl ether is formed. Okay, so you can also form aryl alkyl ether as well. So here we have taken sodium phenoxide. So this was alkoxide which we have taken. Now we are taking a phenoxide and a alkyl halide, not aryl halide, alkyl halide we are taking. So now what happens is sodium and iodide will form sodium iodide. So the CH3 will come here. So you will get benzene on which you have OCH3. Now what is this called? This is anisole, right? Okay. So in this way also you can form an alkyl aryl ether can be also formed. Clear? Now, the limitations of Williamson synthesis. This reaction is not suitable for the preparation of ethers from secondary and tertiary alkyl halide. You can use primary, secondary or tertiary alkoxides, but you cannot use secondary or tertiary alkyl halides. Only primary alkyl halides can be used. So if tertiary alkyl halide is heated with sodium alkoxide, elimination takes place instead of substitution to form alkene. So we will not get ether. So a tertiary alkyl is taken and the alkoxide is also taken here. So now what happens? So now elimination of hydrogen will take place and you will get an alkene and sodium bromide will be eliminated. So there won't be formation of ether here. So I hope it is Clear, right? Now moving on to the physical properties of ethers. Dimethyl ether and ethyl methyl ethers are gases. All other ethers are colorless liquids. So the lower ones of ethers, that is containing 1 or 2 carbon atoms, they are considered to be gases, right? And the higher ones will be not gases, they will be liquids, right? The bond between the oxygen atom and the carbon atom of the alkyl groups in an ether molecule are polarized due to a difference in electronegativities. Since carbon-oxygen bond is polar, ethers possess a net dipole moment, even if they are symmetrical. Dipole moment of dimethyl ether is 1.3 D. That D stands for dBay, okay? dBay is the unit for dipole moment. And dipole moment of diethyl ether is 1.18 dBay. Okay, so what does that mean? This is the structure of ether, and in which you can see a carbon-oxygen bond. So there is an electronegativity difference between carbon and oxygen. Of course, oxygen is more electronegative. It will have a partial negative charge. Carbon will have a partial positive charge. So because of that, there exists an electronegativity difference. Because of that, there will be a polarity in the bond. So this is going to be a polar bond. Because of that, there will exist a dipole moment also, right? The weak polarity of ethers do not appreciably affect their boiling points, which are comparable to those of the alkanes of comparable molecular mass, but are much lower than the boiling points of alcohols as shown. Okay, so if you are taking other compounds which are having comparable mass to that of the ethers, they all will be having almost a similar boiling point, unlike alcohols which will be having more boiling point, right? So the reason for that we have already discussed, that will be hydrogen bonds which is formed. Okay, so as you can see here, the normal pentane hydrocarbon, it is having 309 Kelvin, which is their boiling point. Now the next one is ethoxyethane, which is your ether. It is 307.6 Kelvin, and you have your alcohol, which is 390. Okay, so if you are comparing hydrocarbon, ether and alcohol, alcohol will of course have the highest boiling point, then ether, then hydrocarbon in the end, right? Now, the large difference in boiling point of alcohol and ether is due to the presence of hydrogen bonding in alcohol, which in detail we have studied in alcohols. Now, lower ethers are miscible in water due to some extent. This is due to the formation of hydrogen bonds with water. So, in ethers also it has the tendency to form hydrogen bonds. So it will be lightly soluble in water, not highly soluble in water. So as you can see, this is the oxygen atom, the two alkyl or aryl groups is here, and this is one molecule of water. So oxygen is having a partial negative charge, hydrogen partial positive charge. So they will form an extra bond which is called as the hydrogen bond, right? The solubility decreases with increase in the number of carbon atoms. So even this we have discussed. More and more bigger and bigger alkyl group or aryl group will be present, means of course the solubility will become lesser and lesser in water, because the alkyl or aryl groups are hydrophobic in nature, right? Now moving on to chemical properties. Chemically, ethers are less reactive compared to alcohols and phenols. Ethers are less reactive. The low reactivity is due to the absence of active sites in its functional group. However, under specific condition, ethers also undergo chemical reactions. So first we are going to see again in the same way carbon-oxygen bond cleavage we are going to discuss. Okay, so when ethers are heated with limited amount of hydrogen halide, a mixture of alcohol and alkyl halide is formed. So this is your ether, to which we are adding hydrogen halide. Okay, hydrogen halide means HX. It can be HCl, HBr, HI, HF, etc. Okay, HF generally won't undergo reaction because it is highly reactive. So what is going to happen? You are going to get alcohol and alkyl halide. So you can see ROR, which is going to react with HX. This is your ether. It reacts with HX to form. What it is going to form? RO, and this hydrogen will attach with this oxygen. So what you will get? ROH, what it is? Alcohol. Now what is left? X and R, that is RX, which is your alkyl halide. Clear? Now C2H5O, C2H5, diethyl ether we have taken here, reacts with hydrogen iodide. So what is going to happen? This hydrogen is going to attach here. This oxygen carbon bond will break. This oxygen carbon bond will break. So C2H5 will be separate, to which the iodine will be attaching here. So you will get C2H5I and C2H5O, and this hydrogen will be attached here. So you will get an alcohol and alkyl halide. So when ethers reacts with hydrogen halides, you're going to get a mixture of alcohol and alkyl halide. The next one is when ethers are heated with excess amount of hydrogen halide, alkyl halides are formed. Okay, when we are taking excess of hydrogen halide, here we are not taking excess of hydrogen halide. So we get alcohol as well as alkyl halide. In this case, only we are going to get alkyl halide, no alcohol. So what is going to happen here? ROR, which is your ether, reacts with hydrogen halide. What you are going to get? Alkyl halide and water will be removed. Okay, 2 moles we have taken here. So this 2H and this O will form the water. What is left behind? R and X. Okay, 2 moles of alkyl halide will be formed. Now C2H5O, C2H5 diethyl ether we have taken, reacts with excess of hydrogen iodide. What is going to happen? You're going to get alkyl halide. Which one? It is ethyl iodide, and water will be removed. Okay. Now the order of reactivity of hydrogen halide will be Hi, HBr, HCl. Okay. Because as we move down the group, that is fluorine, chlorine, bromine, iodine, as we move down the group, the size of the atom increases. Hence its reactivity also increases. So hydrogen iodide will be having the highest reactivity. Okay. Now when hydrogen iodide reacts with unsymmetrical ether, the iodine attaches to the smaller alkyl group. So what does that mean? So we are having an unsymmetrical ether here. CH3, CH2, CH2, CH2O, CH3. So you have methyl here and 4 carbon atoms means butyl on the other side. Okay. So hydrogen iodide is taken. So to where or which alkyl group the iodine will get attached? It will be towards the smaller alkyl group. So you will get methyl iodide, and on the other side the hydrogen will be attached, because this oxygen carbon bond will break. So OH will be formed here. So you will get butanol and the methyl halide. So methyl iodide. So I hope it is clear. Okay. So when hydrogen iodide is being added, the iodine or the halogen will go to the alkyl group, which is the smaller one. Now continuing, however, when one of the alkyl group is a tertiary group, halide formed is a tertiary halide. So if you are taking an ether, one of the alkyl group or aryl group can be tertiary. So in that case, what happens? You're going to get a tertiary halide, right? So here we have taken a tertiary ether, that is CCH3, CH3, CH3. This is a tertiary group, right? And you have methyl. So this is methyl, this is tertiary butyl. So the name is tert butyl methyl ether, to which we are adding hydrogen iodide. So in that case, you are going to get a tertiary halide. Okay. Before we have discussed that iodine will go to the smaller group. But in this case, iodine is not going to the methyl, it is going to the tertiary group itself. Because in this case, if you are taking a tertiary ether, it will go to the tertiary group itself. So it will get attached here and you will get methanol here. So methanol and tertiary butyl iodide will be formed. Now the next reaction is alkyl aryl ethers reacts with hydrogen halide to form phenol and alkyl halide. Now this is alkyl aryl ether. That means you have an aryl group as well as alkyl group. So it is ROR, right? So one R is alkyl, one R is aryl. So this is aryl, that is phenyl, and this R is any alkyl group. It reacts with HX, that is hydrogen halide. What you are going to get? You will get phenol, not alcohol, you will get phenol. That is, instead of this R, this hydrogen will attack here and the R will be attacking the X. So you will get alkyl halide as well as phenol will be formed. Clear? Now during this reaction, alkyl oxygen bond is cleavage. This is due to more stability of aryl oxygen bond due to the partial double bond character. So what you are going to get here? In this case, you can see OCH3 is given and you have a phenyl group. So this is your anisole, right? Which reacts with hydrogen iodide. Hydrogen will be here and CH3I will be formed. That is your alkyl halide. Which one it is? Methyl iodide, right? And phenol will be formed, right? Now moving on to the next set of reactions, that is electrophilic substitution reaction. So what are electrophilic substitutions? In detail we have studied in the last chapter also, as well as in alcohols and phenols, right? So the alkoxy group of aromatic ether is ortho and para directing and activates the aromatic ring towards electrophilic substitution reaction in the same way as phenol. So even ethers, like how it was in phenols, this is also ortho-para directing. We can understand it through the resonance structure. So here also it is ROR dash. So your R dash is your phenyl group here. So what is happening? Oxygen is having extra lone pair of electrons. So what is happening? The lone pair of electrons will be shifted here. This will become a double bond. So electrons is lost from the oxygen. So it is getting a positive charge. Now the bond will become a charge here. Now this charge is shifted to bond. Bond will become a charge, which is shown here. Now the charge is becoming bond. Bond is becoming charge. And in the last, the charge is becoming a bond and the double bond goes back and it becomes the lone pair itself. So in here what you can observe, in one ortho position, para position and ortho position, the negative charge will be there. So the substitution will take place in the ortho and para position. So the first one is halogenation. That means we are going to substitute halogenation. Phenylalkyl ethers undergo usual halogenation in the benzene ring. Anisole undergoes bromination with bromine in ethanoic acid even in the absence of iron bromide catalyst. It is due to the activation of benzene ring by the methoxy group. Para isomer is obtained in more yield. So what we are taking, anisole, which is phenylalkyl ether. This is phenylalkyl, right? So 2 moles of anisole we are taking, reacting with bromine in presence of ethanoic acid. So which is the halogen we are going to substitute here? It is bromine. So it is bromination which is going to take place. So it is simple. Where it is going to be substituted? In ortho position, you will get one product. In para position, you are going to get another product. See, para bromoanisole and ortho bromoanisole will be formed. So already we have studied, if you have ortho and para, which one will be the major product? Of course, para will be the major product because it is symmetric. Now the next one is Friedel-Crafts alkylation. Alkylation means we are going to add an alkyl group, right? We are going to substitute alkyl group. Anisole undergoes Friedel-Crafts alkylation. That is, alkyl group is introduced at ortho and para position. Again, the same position. By reaction with alkyl halide in the presence of anhydrous aluminum chloride. So already we have studied Friedel-Crafts alkylation and acylation. So what is going to be added here? We are going to substitute an alkyl group. So again we have taken anisole and alkyl halide we are going to take. What is going to happen? From this alkyl halide, this alkyl group is going to be substituted in the ortho and para position. So you get 2-methoxy-toluene and 4-methoxy-toluene. So now comparing ortho and para, again para will be the major product because again it is symmetric. Okay. So one in the ortho and one in the para position substituted product you are going to get. Alright. Now the next one is Friedel-Crafts acylation. Okay, acylation means what? We are going to add acyl group. So when anisole is treated with acetyl chloride or acyl chloride in the presence of anhydrous aluminum chloride, ortho and para derivatives is obtained. Again, we are going to take anisole. Instead of here, we had to substitute alkyl group. Here we are going to substitute the acyl group, which is CH3 C double bond O. So this is your acyl group in presence of again anhydrous aluminum chloride in presence of carbon disulfide as well. So this much part COCH3 will be substituted in ortho and para position. So of course again the para one will be the major product. Clear? So there will be no change to the OCH3 alkoxy part here. Only the reagent that we are going to add will be substituted in the ortho and para position. Now next one is nitration. So what is nitration? We are going to introduce nitro group. Anisole reacts with a mixture of concentrated sulfuric acid and nitric acid to form a mixture of ortho and para nitroanisole. So anisole, so we have taken anisole here. What are we going to do? Nitration. Nitration means nitrating mixture we have to use. What is nitrating mixture? A mixture of concentrated sulfuric acid and nitric acid. So what is going to happen? Nitro group is going to be substituted in the ortho and para position. So you get 2-nitroanisole. That means ortho anisole you are going to get as well as para nitroanisole you are going to get. Okay. So by this we come to an end to this chapter. So in this session we have discussed all the physical and chemical properties of ethers and we have completed the ethers as well. Okay. So I hope the concepts that I've covered in this chapter is clear for you. So that's all for today. Thank you.